It was businessman Warren Buffett who said, risk comes from not knowing what you're doing. In this lesson, we're going to determine the break-even prices and amount using technology or algebra. All to answer the question, what happens when revenue equals expense? Before we get into it, let's make sure we're ready for this lesson by taking a look at warm-up number 2. Graph each on the same set of axes. So if I just go ahead and make my xy axis, y is equal to x squared is a parent function parabola that goes through the origin. It's positive, so it opens upward. Y is equal to negative 2x has a y-intercept of 0 and a slope of negative 2, so we can go down 2, right 1, and this will give us our line. Now, let's take a look at a problem you will be able to do by the end of this lesson. The student government at State College is selling inexpensive bookcases for dorm rooms to raise money for school activities. The expense function is E equals to negative 200p plus 1,000. And the revenue function is R is equal to negative 18p squared plus 800p. Determine the price at the break-even point. We have an Excel spreadsheet that will allow us to do this. In the command bar, you can see what I put in as the B2 equation. You can also, in the command bar, see what I put in the B6 equation, into the B10 equation, as well as what I put into B15 and B16. This is going to give us the prices of $13.08 and $42.48. When the revenue function is the quadratic equation, you can determine the values at which the expense and revenue functions are equal. Graph the revenue and expense functions on the same coordinate plane. The functions intersect at the value at which the expense and the revenue functions are equal, those blue points, or the break-even points. The difference between expense and revenue equals 0, which is the zero net difference. Notice that the price on the revenue function between the break-even points results in a revenue greater than expense. Prices beyond the break-even point result in revenue less than expenses. Decision makers must examine the break-even points carefully to set appropriate prices to yield maximum revenue. Break-even points may be found algebraically or by using a graphing calculator. To find break-even points algebraically, set the expense and revenue functions equal to each other. Rewrite the resulting equation with 0 on one side of the equal sign and all the remaining terms on the other side. This gives you the quadratic equation in the form ax squared plus bx plus c equals 0, where a is not 0. The quadratic formula can then be used to solve the quadratic equation. The quadratic formula is that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, where that plus or minus reads as two solutions, both plus the square rooting and minus the square rooting. Visually, the break-even points occur when the expense and revenue functions intersect. If a graphing calculator is used, let x represent the price, and express the equations in terms of x. Enter each function into the calculator and graph them both using suitable viewing window. Find the intercept points. Because the calculator will display answers to many decimal places, round the intersection point to the nearest hundredth, the nearest cent. Break-even analysis can be used to make product price setting decisions. Calculations and interpretation must be done during break-even analysis. Let's determine the break-even price. Determine the prices at break-even points for the Picasso Paint product that we did in the last lesson. This is the expense function and the revenue function. So the break-even points will occur when these two equations intersect. These figures show two graphing calculator screens after the intersection feature has been used. Shown on the left is the leftmost break-even point. At that point, the price is $8.08. On the right is the rightmost break-even point, and at that point, the price is $58.92. Both break-even points have been rounded to the nearest cent. To find the break-even points algebraically, you're going to set the expense and revenue functions equal to each other so that E is equal to R. We're going to rewrite the resulting equation with 0 on one side and all remaining terms on the other side. And the quadratic equation is usually written with the leading coefficient being positive. So we get negative 3,500p plus 238,000 is equal to negative 500p squared plus 30,000p. So if we want to write this all on one side with a positive p squared, we will have 500p squared minus 33,500p plus 238,000 is equal to 0. To make life a little bit easier, let's divide everything by 500. This is going to give us p squared minus 67p plus 473 is equal to 0. So now we just have some smaller numbers to deal with. This means that A is 1, B is negative 67, and C is 473. So P would be equal to negative times negative 67 plus or minus the square root of negative 67 squared minus 4 times 1 times 473, all of that square rooted, all over 2 times 1. This does mean that there are two versions of this answer. One where P is equal to negative times negative 67 plus the square root of negative 67 squared minus 4 times 1 times 473 divided by 2 times 1, and P is equal to negative times negative 67 minus the square root of negative 67 squared minus 4 times 1 times 473, all square rooted, over 2 times 1. Solving the positive version of this gives us P is approximately $58.92. That's because we're rounding to the nearest cent. And on the negative version, we get that P is approximately $8.08. So the price of the break-even points are $8.08 and $58.92. Let's check our understanding. The expense function for a particular product is given here. The revenue function for that product is also given here. Determine the prices at the break-even points for the product algebraically or graphically. So the first thing we're going to do is set E equal to R, which means writing both equations, negative 2,000p plus 125,000 is equal to negative 600p squared plus 18,000. I'm going to move everything to one side, making sure that my p squared is positive, so that I get 600p squared minus 20,000 p plus 120,000 or 125,000, and this is equal to 0. I can make all of these numbers smaller by dividing by 100 to get 6p squared minus 200p plus 1250, and that's equal to 0. So the p will be equal to negative times negative 200 plus or minus the square root of negative 200 squared minus 4 times 6 times 1250, all square rooted, all over 2 times 6. This means that we do have two separate answers. One where P is the positive version, so P is negative times negative 200 plus that square rooted divided by 2 times 6. And that P is negative times negative 200 minus that square rooted all over 2 times 6. This will give us that P is $8.33 and that P is $25. Let's extend our understanding. Suppose you notice that each of the terms in the quadratic equation is divisible by 500. Factoring out 500 from each of the terms, then dividing both sides by 500 yields the quadratic equation p squared minus 67p plus 476 is equal to 0. Either using a graphing calculator or the quadratic formula or this method of completing the square to determine if you come to the same break-even points as the first example. And as it turns out, that was just a natural way to go ahead and do it during the Check Your Understanding. Determine the revenue and expense for Picasso Paint product at the break-even point found in example 1. The Y value of the break-even points will be both the revenue and the expense values. These values can be determined by substituting the value of P into the expense and revenue equation. So if we look at the expense equation, that would now be negative 3,500 times 8.08 plus 238,000. And this is going to give us 209,720. For the revenue function, we would have negative 500 times 8.08 squared plus 30,000 times 8.08. And that's going to give us 209,756.80. Now, if we're substituting 5892 in for P, then we would be looking at an expense function of negative 3,500 times 58.92 plus 238,000. And that's going to give us 31,780. The revenue function would be negative 500 times 58.92 plus 30,000 times 58.92, and that would give us $31,816.80. When the break-even point is $8.08, the expense value is $209,720, and the revenue is $209,756.80. Both are close to that $209,750. When the break-even price is $58.92, the expense value is $31,780, and the revenue value is $31,816.80, and both are close to that approximate $31,800. Because of rounding, the expense and revenue are not equal. They are, however, approximately equal. Let's check our understanding. How could you have reduced the error when calculating the expense and revenue values? The error could have been reduced by using more accurate prices with more decimal places in the calculation. But for this purpose, it's accurate to round to the nearest cent. Use a spreadsheet to determine the break-even price for Picasso Paint products. We develop a generic expense and revenue function so the spreadsheet can be calculated and the break-even points in a similar situation. The expense function of E is equal to VP plus F, where P equals price, V equals variable cost, and F equals fixed cost. The revenue function R is equal to AP squared plus BP, where P equals price and A and B are values specific to a particular situation. We set the expense functions equal to the revenue functions. Depending on the spreadsheet software, cell formulas may vary. The Picasso Paints function of E is equal to negative 3,500p plus 280,000, and R is equal to negative 500p squared and 30,000. The values of V and F from the expense function are entered into cells B3 and B4. The values for A and B from the revenue function are entered into cells B7 and B8. Cell B15 and B16 are the break-even points calculated using the quadratic formula. For B15, the formula can be seen in the command bar. And for cell B16, the formula can be seen in the command bar. Let's check our understanding. What cell formulas were used to identify the A, B, and C values shown in B11, B12, and B13? Here we can see the formula used for B11. Here is the formula for B12. And the formula for B13.